of our design. Like after geometry, we have to go for winding. Open that saved model and then go for winding. That we will have two options like pattern and definition, coil style, divider type, winding definition, model, and this is the pattern of your winding type, like automatic, custom, or path type like center, layer. Number of throw. If you change the number of throw, you can see the change in the linear pattern phasor. Even harmonics are the factors. So these things we can also check by changing this number of throw, number of turns, number of parallel path. Like if torque is, if you required more torque, then you have to change your like winding pattern in that like power. Sometimes power is required more, speed is more required, torque is, so we have to make the power. We know the power is equals to torque into omega, so according to that, like if power is constant, we basically have to play with the torque and omega. And if you want to increase one parameter, you have to decrease the other parameters. So according to that, we have to do the winding, changing the current value for the torque. There's a linear pattern look, phase one, phase two, phase three. Phasor, phasor diagram. 12 phase. So you are getting the phasor diagram like this. Then we will check on the harmonics and the factors. So one by one, we have to select, like if you want your winding to be customized, so then we have to click on the custom. So this is the harmonic value. For first, we are getting 0.9576, and for third 0.6. So if you change the number of throw and number of parallel path, you can also see the change in the magnitude of harmonics. Seventh harmonic is 0.157. So this is the winding layer. Change the layer reduces the harmonics. But when we are designing your machine, we have to think about the torque ripple value. So if I will increase the value of winding layer, and the torque ripple will increase, so that also we have to consider. Like means there are many parameters. We, according to that, we have to design, like we have to somehow make a trade-off between the all the things. Like if I change something, their effect will be in the output. So so that we have to make changes according to that. Wire diameter, copper diameter, linear thickness. So these are the parameter we have to set when we are designing our winding, like number of strand in hand, and according to the copper diameter, we have to set the values. Like we have to basically fill our slot. Whole slot should be filled, not exceed the value should not exceed the area which is already provided. So according to that, now you can see the number of conductor per slot is reduced and the copper diameter is reduced to 1.1. So that we have to think about, like copper depth also you can set up to 100%, not more than that, or less than. Basically you have to, like the copper depth should be. And then we have to set the copper slot fill option we have to do. So this is the winding, and then geometry we have to go for input datas. So these are the laminations, like stator lamination, black iron. You are using M350 50 ampere capability, and then the other is the armature winding is as a copper pure. So this is the electrical resistivity, and this is the list of component material from the database. And even you can also add your material from the database, that also is possible. So, and the next is the electrical resistivity, temperature coefficient, and if the magnet would, like you are designing the magnet material or magnet motor with the magnet, so then we have, you can see the magnet bar values, magnet relative permittivity for the BLDC motor or PMSM motor when we will design. So these two columns will be filled at that time. And then this is the density of the, according to density and according to the we are basically calculating the weight of the machine is 45.87 for that machine. So if we change, like in material from the rotor cage from iron, like aluminum to copper, now if we change that, now you can see the value of weight is increased to 51.7. That was 48, now it is 51.7 kg weight. So according to that weight, or according to that, like we have to think about the considering the parameter according to our requirement. Means weight is not a constant, then we can increase the weight and going towards the more efficient motor design. Sometimes we have the size is not the constant, then we can go for the bigger motor with less cost. You can also see the individual weight of the stator, individual weight of the rotor. So we have covered the geometry part, we have covered the winding, being for the induction motor. In the winding we have pattern, we have definition, and then we have completed the input data of the material. Now we have to save our model geometry with material. Now we will do the electromagnetic analytical analysis. So geometry part we have covered. We have covered the winding. We have covered the input data. Now we will go for electromagnetic analysis using FEA method. So I will little bit forward this one. So we will have to save our model first for the winding, and now we will go for calculation. In that calculation tab, you will find options like how you want to drive your vehicle, or how you are to drive your motor. So for that we have the driving mode, motor generator, and brake. And you have to set the operating point definition like speed, slip, torque, frequency. So according to that we have to set the value of the like 400 for our vehicle specification. So we will set it as the DC 400. Supply definition we have to set as AC or inverter feed. So right now we are working for the inverter feed, so we will set it as the inverter feed. Change the value of the current, RMS 900. SQ definition for the rotor, 5%. Change the temperature also, like safe temperature it is 20, so that also we will change. Now we have the option in the saturation mode like analytical or FEA. So first we will go, we are doing the analytical. If you want, you can also select the FEA and do the FEA analysis. The process will be same for both analytical and FEA analysis. So we just go with the analytical, and then you can go, or I will also show you how we can do that for the FEA. So same process we have to follow, only we have to click on the FEA analysis, and then we have to click on the calculate saturation method. Here I have to change the maximum RMS current first, and then I have to click on that. Now we are interested in 900, so we will change that. Now we have to click on the solve e-magnetic model.
So here the temperature, the maximum limits that how much maximum temperature can withstand the motor.
That you can see even we do the thermal analysis of the motor. There you can see, okay, right now we are giving information of 100 only, but at that time it will increase to certain extent more than that 100. So that value is the maximum temperature your motor will go. That will be visible in thermal behavior of your motor designing. So first we basically, like you can see the next two electromagnetic, we have the thermal. So there thermal, we have to click on that, and according to that you can see the level of temperature it will able to reach. So maximum speed we have to fade as 14800, RMS current 900, and we want our saturation or loss model to be considered. So we have to first build a model, click on that. Now the saturation losses for the analytical method is considered, and iron losses. According to that, we will get the result. So this is the model status. Saturation and iron loss is added. Number of pole is 6, slot number 72. Now you can go to the loss model. So here we have to set the DC resistance per phase is automatically calculated. Now go to calculation. So these calculations already DC bus voltage we have already set it as a 400, so that is already present, and the reference temperature for the stator winding we have set it as 100, and this is the lost build factor, so that we will consider it as 1 for the stator and the rotor. And mechanical loss, right now we are not neglecting that. If you want, you can also add the frictional loss, you can also add the windage loss. And if you want, you can also click on the motor generator, both operating mode. Now click on the efficiency map, and for that we have set the maximum. We have to set the maximum speed, and even the speed should be in this range, like step also we have to fit. So this is the current value and the step to reach that current value, like number of increment in our graph. We are setting these things because we basically want our graph to look familiar, more familiar and more informative. Click the calculate electromagnetic performance, so it will take some time, so I will fast forward, little bit fast forward this. So now you can get the efficiency map will look like this, like we have the shaft torque, we have the speed, so and the efficiency. Now you can see the when you are for this motor, when the speed is more than 400, you are getting the efficiency more than 90%. And this is the shaft power. So at low speed you are getting a very like efficiency is very low for the low speed, like at least the motor should run at more than 200 rp 2000 rpm. And you can also click on the point to get the exact result, like x y z. Z is the efficiency, so you are getting at that particular point, you are getting for that particular speed you are at 93% efficiency. Speed 9500, for that power you are getting as a 3/4. So after increasing the speed, the little bit there is a decrease in power also after 10,000. So according to our application or according to our use, we basically have to design our machine to reach that level or to see the values of the torque or the power. And this is the duty cycle part. You have the options like custom duty cycle or automotive drive cycle basically. So we can also set that, and you have options like US, Japan. So these options are available for you. Like we will select as US 06. You can also add by custom duty cycle, you can also add your drive cycle like Indian drive cycle or your locality drive cycle, if you duty cycle, if you have that information, speed, or your like your college, your campus values, that also we can fit here. Or now what we are doing, we are by using the vehicle model, so we will change the mass of the vehicle, we can change the frontal area, we can change the wheel radius, drag coefficient. So these things we will add to get the duty cycle performance.
So actually, sir, so we can calculate na, this all the type of calculation, let's say for
Yes.
any vehicle.
Yes, any vehicle, but but we need these information like masses, or when we are running our vehicle in our campus or anywhere, you will get the velocity versus like RPM graph. So from there also we can create. So that will be helpful when you are creating the custom duty. Then that will comes under the custom. Otherwise, you have to follow this according to Indian drive cycle. We have to put the values.
Okay.
So click on the calculate duty cycle performance. So it will take some time, so I will fast forward this one. That's why I'm recorded this session, and using that like to use the maximum utilization of timing. So we just have to click on the like shaft torque and the time curve you are getting for the machine, which in for the machine information which we fed like weight or the other thing. And this is the average efficiency for that particular drive. Losses, total loss, copper loss, iron loss, mechanical losses, motor operation. Load result view. And we are putting the value drive cycle in the efficiency. Because of blue dots are for the drive cycle. So right now you can see the values from 0 to 200 RPM, so getting very less speed. At that time, very like for that particular drive cycle, you are getting the less efficient. Now when you can see the cluster of the drive cycle comes under the 6,000 to 8,000 RPM. So there you are getting the more efficiency, like more than 90% at that part. And for one particular operating point also we can check like speed to 6,500 and the torque also if you change 370, and then we can calculate the operating point. Right now we have not doing lap coupling with the thermal behavior we are not adding, but we are adding the operating point with e-magnetic analysis. So just to calculating according to the losses like iron loss and the copper loss, according to that you are calculating the operating point. So for that particular speed and for that particular torque, your shaft power will be 2.5 10 to the power 5, and then phase current value like 900, we are maximum RPM, like RMS value of the current we are setting is at 900. So now, so this is the 888 it is utilizing. Frequency, supply frequency is 328 hertz to achieve that, and efficiency is 92.63. Now go to E-magnetic. So we have covered E-magnetic, then calculation part. There you can see also like 900 we have fed at the maximum RMS, but for that 900 it is taking for this drive we are, it is taking as 888.2. Now for this particular operation like 6500 and 370 torque value, so we can solve the E-magnetic model. Now for this particular value like 400 volt ampere, 888.2 supplied. This one no load input power fundamental frequency 380%. So slip is set to 0.091, drive frequency 328. And this is the other variables like air gap torque value, shaft torque value, mechanical output power, efficiency 92.6 that we already shown. And then the other values you will get it like this only, like ending current, core losses, current. We can also change the unit by going to the default and change the unit like power to kilowatt. Now you can see the value. So similarly, first you can see the values in the like equivalent circuit model will be created. So in that equivalent circuit, like the stator and the rotor will look like this: stator value, rotor value. You can also see the values of the power for each component. You can also see the voltage across each component. You can see the values, you can see the name in the component. So this is the T circuit. So you can also, for the L circuit also, you can see the equivalent circuit value like for the R1 for the stator and X1. So these values will be calculated, and this when you circuit equivalent circuit for your induction motor will look like this. And circuit for the rotor. So if you click on the value, now you are getting the value for the current value 888.2. And this is the flux density part. Similarly, you can go for checking the values for the losses also like 12.38, and how we can remove and make the losses to be less value. So these things you can see in the loss tab, you can see. And this is the graph. In the graph tab, if you click on the graph, you can see the graphs value like air gap flux density. And this is the calculation part which we covered. In that you can We have set the motoring mode, we have set the operating definition. Now we will save our result as a e-magnetic result. Okay, if you have any question you can ask.
So is there any feasible to find out the optimal size? That what will be optimal size of the winding? What will be the optimal size
By
of the...
in MotorCAD you have one tab like okay, is my screen visible?
No, sir.
Or wait, just give me a second. Now you can see in this sensitivity option is there. In that sensitivity option, if you click on that sensitivity, so then we have to make the parameters, and according to that we have to set the size parameter, what is required, like the power value. According to the power value we have to set the size of the machine, like power and the velocity of the calculation. We have to do like analytical method when we will do for the machine, so then we will get the result of the sizing. Optimization of size you can do, means you have to connect MotorCAD with the answers. OptiSlang is there for the optimization, and then you can do the like complete analysis of the optimization. If you connect only sensitivity of the MotorCAD, then you can able to see only you can able to see only the parameter wise, like one and one parameter wise, like or multi parameter you have to select, and then you can see the size for that particular size of the machine, what are the results you are getting. So here you can say we have the trial and error type of analysis you have to do by using the sensitivity. But when we'll do the like optimization using the OptiSlang answers, OptiSlang, there we can do that.
And you one thing you mentioned that we are giving the supply from a DC bus and
Yes.
to the induction motor. So inverter part we can also design the inverter part because...
That I also show you how we can like this is the motor design tool, but in the next session I will show you like design your motor and then how you can connect with the inverter. So that we will cover in the next session.
But in this CAD, how we can defining that? Because the input I'm giving DC and output we are giving to the induction motor. How we can define? How we can consider the effect of the inverter in this CAD?
By default, in inverter is connected in that. So by using that by default method, they are basically calculating. But we what we generally do, we will design our machine in MotorCAD, and then we will do all the analysis of the controlling in the ANSYS Twin Builder. There we will do all the analysis. We only here we are only checking the default inverter is there with the six leg, like three leg in six phase, three phase inverter is there. So on that it will automatically calculate the value of the frequency for this design. Like we got now 325 hertz, so that
Yes, sir.
frequency it
Yes,
will
sir.
automatically, yes, so that automatically it will select and then design and get the give us the efficiency related, like designing that value will be automatically calculated. But that we have, if you want to go in deep detail or if you want to do the designing for that we will do by using the ANSYS Twin Builder is there. So in that Twin Builder we will design, or simpler we will see how we can go for designing and controlling our BLDC or in induction motor or any other machine.
Okay, thank you, sir.
Should we take a break or are you continuing, sir?
We are basically waiting for Q&A. If there is no Q&A, then I will take a break and then we will reconnect.
Okay. Does the student version also have all those what you have shown here? So because some participant had asked in the chat, is sir using the same software what we have installed?
For MotorCAD, they basically have to download the trial version of the MotorCAD.
Okay.
So they have to download it for the trial version of MotorCAD by
And then
using their ID, and then they can do that.
okay. So like participants, like if you want to do this MotorCAD thing, what sir did, you have to go for the not the student version, you have to go for the trial
Trial
version itself.
version.
So the trial version, do you have the inverter and the other motor design also?
Ma'am, they will find their other
All options.
options,
Okay.
all options.
So for trial version, how long is it? Is it for a year or is it only for
Uh,
faculty or what institute ID? How is it?
yeah, I think it will be useful by using the institute ID.
Institute ID. Okay. So participants also having your institute ID through the you can go and download the trial version where all the other options will be there. For students version, like then what was the thing like we would have gone for the trial version itself. Why did we go for the student version? What is the
Uh,
advantage of that?
no, MotorCAD. There is a separate like ANSYS, and the MotorCAD is like ANSYS acquired the MotorCAD, but
Okay.
MotorCAD are basically running separately. That's why they are providing in the format. Like you can say the trial version is there. Otherwise, in for the other ANSYS tool like ADT, there is no such trial version is present right now.
Okay. Okay, sir.
Think we don't have any query right now. If anyone having any query, they
So for
can write it
one
in the
more thing,
chat
I
box.
just want to know for the EV solution complete also that MotorCAD will be useful now if we download the trial version.
If that will be like you can connect with the for the like you have designed your machine, but after designing you basically want connection with the like sir has some doubt in the related to like you have to design inverter, DC boost converter or buck converter. So that for that you required a simpler or twin builder. Then you can do the whole analysis, or by using RM expert also you can design your machine.
So now I'm asking the trial version for those things are also available.
That interconnection between twin builder and the MotorCAD, that I need to check.
Okay. Okay, sir.
Yes.
Yeah, participants, I think then we can take a short break and come. Is it, sir?
Okay, ma'am. So we will connect at 11:30. Na?
Yeah, yeah. So participants, you can take a short
Okay.
break till 11:30 and sharp 11:30 we will start this session. And one more thing, like the valediction also we are starting at 2:30 itself because I got the information from sir that he's not joining ABB. Like he's traveling, he has a sudden trip and he had to go. He was traveling. So at 2:30 we will have the valediction also. So all the centers be ready. We will have the test and the feedback at the same time, and after that I'll be just asking your feedback, so that will be in the afternoon session from 2:30. Yeah, now you can take a short break till 11:30.